Hello student, my name is Nimish Prabhakar. I am Assistant Professor at LJ Institute of Engineering and Technology in Instrumentation and Control Department. Welcome to Process, Dynamic and Control lecture series.
Now in this lecture, non-interacting system and interacting system. So, what is non-interacting system? What is interacting system? We will discuss about this in this lecture. So, before starting about this, first of all, one question: what are the ways to get a second order system? So, my question is how we can get the second order system? So, there are number of ways to get second order system. So, first one way is series connection of two first order system. That means by connecting a two first order system in series, we can get a second order system. So, this is the simplest method of getting second order system. Now, second way is to get second order system is first order system under feedback control. That means if any first order system and we give a control, like we give a feedback control, then that system is known as the second order system. That means we know the CSTR or CSTH is the first order system, and to control the temperature or the flow rate, that means to control the temperature or the height inside the tank. So we provide a one simply when we put a one controller. So that type of system, it become the second order system. So we can get the second order system by putting the control and the feedback in the first order system. And last one way is the inherently second order system. That means in my previous lecture we discussed about the inherently second order system, that is the U-tube manometer. So this is the example of the inherently second order system. So these are the ways to get the second order system. So first one way is the series connection of the two first order system. Then we can also get by first order system under the feedback control. And third one, we can get the inherently second order system. So now in this lecture we discuss about the first one, series connection of two first order system. So there are two ways to connect the series connection of a first order system. That means we can connect two first order system by non-interacting method, and we can also connect two first order system by interacting system. So here first we discuss about the what is the interacting system. So in this system, change in second system does not affect the first system. Now we understand by help of one example. See here, this is a first order system and this is also first order system. That means here we take the one example of the liquid tank system, and these two tanks we connect in the series. Now here we connect two tanks. At that way, the change in the second system, that means here the change in second system does not affect the first one system. That means here if we increase or decrease the height of the liquid inside the tank, it does not affect on the first one system. So this type of system is known as the non-interacting system. Now we discuss about the second one type of system is the interacting system. Now in this system, change in the second system does affect on the first system. So now we understand this by help of the figure. So here we also take two first order system. Here the first one is the liquid tank and second one is also liquid tank. But here we see the connection is slightly different from non-interacting system. That means here the change in second system does affect the first one system, because here if the liquid level is changed, then it also affect in the first one system of the liquid level. So this type of system is known as interacting system. Simple definition: non-interacting system, that means the system in which the second system does not affect the first one system, and interacting system is the system that the second system does not affect the first one system. Okay. Now we derive the transfer function of the non-interacting system. So for the non-interacting system, this is the figure of the non-interacting system, and here we derive the transfer function of the non-interacting system. So here A1 and A2 is the uniform cross-section area of the tank 1 and tank 2. That means this is a tank 1 and this is a tank 2. This is a uniform cross-section area of the tank 1 and uniform cross-section area of the tank 2. Now R1 and R2, this is the R1 and R2 is the flow resistance of the tank 1, and this is the R2 is the flow resistance of the tank 2. Q is the inlet flow of the tank 1, this is the inlet flow of the tank 1. Q1 is the outlet flow of the tank 1. Here the Q1 is also the act as the inlet flow for the tank for the tank 2, here the tank 2. So this is the inlet flow for the tank 2, because the Q1 goes into the directly to the tank 2. So this is also Q1 is also the outlet flow of the tank 1 and also the inlet flow of the tank 2. Now Q2 is the outlet flow of the tank 2, and H1 and H2 is indicate the level of water inside the tank 1 and tank 2 respectively. Now here the outflow from the tank 1 discharge directly to the tank 2. That means here the outflow Q1 is discharged to the directly to the here tank 2. Now what is the aim? So here our aim is to determine the transfer function that relate the H2 to Q. That means here we have to find out the H2S upon QS. That means here we find out the transfer function of the H2S by QS. Now we know for the single system we find out the transfer function for the H1 by QS. Now here we find out the H2S by QS. Now we start procedure. Now here first one we take some assumption. So first one assumption is the liquid is of the constant density. That means the liquid density is the throughout the tank 1 and tank 2 is the constant, and the tank has the uniform cross-section area. That means tank 1 and tank 2 has the uniform cross-section area, and resistance are linear. That means it acts as a linear behavior. That means here R1 and R2 is the linear resistance. So these are our assumption. Now we start procedure. Now first one we go for the mass balance around the tank 1. So we know the mass balance equation for the tank 1. Inlet minus outlet is equals to accumulation. So here directly we put the inlet is the Q, outlet is the Q1, and the accumulation is the A1 dH1 by dt. Okay. So here the rho is constant, so we have the delete here. So now this is the mass balance for the tank 1, same as we discussed in the liquid level system, energy and mass balance system. Now mass balance around the tank 2. So here we can also write the mass balance around the 2 as the Q1 is the inlet, Q2 is the outlet, and the rate of accumulation is nothing but the A2 into dH by dt. So this is the mass balance around the tank 2. Now the flow head relationship for two linear resistance are given by, that means we find out the relationship for the R1 and Q1 and R2 and Q2. So as we write in the liquid level system, same as we can write the Q1 is equals to H1 upon R1, that means here the Q1 is nothing but the H1 upon R1 and the Q2 is nothing but H2 upon R2. Now, by introducing deviation variable and steady state condition and taking Laplace transform of this equation, we can write, so here we take the steady state condition and now we can write the Laplace transform. So as the Q1s is equals to H1s by R1 and Q2s is equals to H2s by R1. So here we define first deviation variable, first we define the steady state condition, then we define the deviation variable, and then after we take the Laplace transform. So we know the procedure of the steady state value. So here the Q1s indicate the steady state value of the Q1, and this is the difference between the Q1 and Qs is nothing but the Q, and after taking this Laplace we can write the Q1s. So same as we write about the H1s, Q2s and H2s. So we get the equation 5 and 6. Now at steady state, equation 1 become, that means this equation become Qs minus Q1s is equals to 0, because we know that at the steady state there is no accumulation, that means there is no change in the liquid height. So this term, derivation term is 0. So A1 into 0 is nothing but the 0. So here we write the steady state value of the equation number 1. Qs indicate the steady state value of the Q and Q1s indicate the steady state value of the Q1. Now subtracting the equation number 1 from equation number 7, that means from this equation we subtract this equation. So we can write Q minus Qs minus Q1 minus Q1s is equals to A1, and we also write this H1 in the steady state form. So we can write d by dt H1 minus Hs. Okay. Now here we define the deviation variable Q minus Qs nothing but the capital Q, and Q1 minus Q1s is nothing but the capital Q1, and this is the H1 minus S, so we can write the capital H1. So A1 dH1 by dt. So this is the equation for the tank 1. Same as we can write the equation for the tank 2. Q1 minus Q2 is equals to A2 dH2 by dt. So this is the equation for the deviation equation or the steady state equation for the H2. Now by taking the Laplace transform of the equation number 8, so now here we take the Laplace transform of this equation. So we can write Qs minus Q1s is equals to A1, and we know the Laplace transform of the derivation term is the S H1s. So we get this Laplace transform of this equation. Now by putting the value of H1s from equation number 5, so instead of this H1s we put the value of H1s from equation number 5. So this is the equation number 5. So here we put the value of H1s. So we know by the H1s nothing but the Q1s into R1. So instead of here the H1s, we put value Q1s into R1. So we get the Qs minus Q1s is equals to A1s into instead of this H1 we put here the Q1s into R1. Okay. So now here Q1 is from this side and this side Q1 is common. So we can write the Qs is equals to Q1s is common A1 R1 into S plus 1. So we can write this equation as Q1s upon Qs is equals to 1 upon A1 R1 S plus 1. So we can define this equation as Q1 S into upon Qs is equals to 1 upon tau 1 S plus 1. So here tau 1 is represent nothing but the A1 R1. Now same as we can write equation for the tank 2. So for tank 2 we can write equation as the H2S upon Q1S is equals to R2 upon tau 2S plus 1. Here the tau 2 is represent the A2 into R2. So we get two equation. This is a equation, this is Laplace transform equation for the tank 1 and this equation for the tank 2. Now by multiplying these two equations, like this equation number 8 and this equation number 9, we get the Q1S upon Qs, H2S upon Q1, and this is the value of the first term and this is the value of the second term. So here by Q1S and this Q1S is cancelled. So finally we get the H2S upon Qs. This is our aim. To find the transfer function of H2S upon Qs is nothing but the R2 tau 1s plus 1 tau 2s plus 1. So this is the transfer function of non-interacting system. Here the overall transfer function of equation number 10 is the product of the two first order transfer function. That means this is nothing but the overall transfer function is nothing but the multiplication of the first order first term and that means the two first order system multiplication. So this is the non-interacting system. So now here we discuss about the interacting system. So now we start for the interacting system. So this is the interacting system. Same as we discussed in for the non-interacting system, A1 and A2 is the cross-section area of the 1 and 2. R1 and R2 is the flow resistance of the tank 1 and 2. Q is the inlet flow rate of the tank 1. Q1 is the outlet flow of the tank 1. Q1 is also the inlet flow of the tank 2. Here consider tank 2. And Q2 is the outlet flow of the tank 2. And H1 and H2 is the respectively height of the water level inside the tank 1 and tank 2. So here the flow through the R1 now depend on the difference between the H1 and H2. That means here the flow R1 depends on the H1 and H2, hence the variation in H2 affect the variation in the H1, because we know this is the interacting system. So aim is also same as the non-interacting system, to determine the transfer function of the relation between the H2 to Q, that is nothing but the H2S upon Qs. So assumption is same as in the non-interacting system. So we start here for the interacting system. So mass balance around the tank 1, we can write Q minus Q1 is equals to A1 dH1 by dt. Now mass balance around the tank 2, we can also write same as Q1 minus Q2 is equals to A2 dH2 by dt. So the flow head relationship for the R1 is given by, see here, this is just slightly different from the interacting system, from non-interacting system. So here the Q1 is nothing but the difference among the H1 minus H2 upon 1 upon R1. So this is a different from the non-interacting system. And the same as we can write the flow head relationship for the R2 is the Q2 is equals to H2 upon R2. So now we define the deviation variable, and taking the Laplace transform, we can write this equation as the Q1s is equals to H1s minus H2s upon R1, and we can write also this equation as the Q2s is equals to H2s upon R2. So this is we get these two equations. Now at steady state, equation number 1 become Qs minus Q1s is equals to 0, same as the non-interacting system. Now with subtracting the equation number 1 from equation number 7, we get Q minus Qs is equals to Q1 minus Q1s is equals to A1 dH1 minus Hs upon dt. So now taking the deviation variable, we can define the Q minus Qs is equals to Q minus Q1 minus Qs is nothing but the Q1 is equals to A1 dH1 upon dt. Now same for we can write for the tank 2, Q1 minus Q2 is equals to A2 dH2 by dt. So by taking the Laplace transform of the equation number 8 and equation 9, that means these two equations, this equation number 8 and this equation number 9, we can write this equation as Qs minus Q1s is equals to A1 s H1s, and for the equation number 2 we can write Q1s minus Q2s is equals to A2 s H2s is equals to equation number 11. So we get these two equations from the Laplace transform of these two equations. So now here we have 4 equations, like Laplace transform of the tank 1, Laplace transform of the tank 2, and for the valve 1 we can write here we know the Q1s is equals to H1s minus H2s upon R1. So R1 is goes to the multiplication. So we can write this for the valve 1, and for valve 2 we can write the R2 into Q2s is equals to H2s. So now solving this 4 equation, we get the Laplace transform of the interacting system, and we can also say this equation may be combined to eliminate the Q1, Q2 and H1 to arrive the desired transfer function as H2s upon Qs is equals to R2 upon tau 1 tau 2 s square plus tau 1 tau 2 plus A1 R2 into s plus 1. So this is the final equation for the interacting system, or we can say this is the transfer function equation for the interacting system. So in this lecture we discuss about the non-interacting system and interacting system.